Greetings, fellow cosmic voyagers. Settle in, find your rhythm, and prepare to embark on another profound journey into the very fabric of existence. Tonight, we delve into a concept that challenges the fundamental limits of how we traverse the immense void: field propulsion. Imagine spacecraft that don't carry their fuel, but instead push off the universe itself. This is a story of audacious dreams, rigorous science, and the tantalizing possibility of truly boundless exploration. As we unravel these mind-bending concepts, remember to like, comment, and share this voyage with others who seek to understand the universe. Let the narration begin. From the vast emptiness between galaxies to the intricate dance of particles within an atom, the universe whispers secrets of unimaginable power. For centuries, humanity has dreamt of harnessing these secrets, not just to understand our cosmos, but to travel through it. We've built towering rockets, defied gravity with fiery plumes, and launched ourselves into the cold vacuum. But what if there was another way? A way to sail the cosmic winds, to push off the very fabric of space-time itself? Welcome to Vibing Science. I'm your guide, and tonight, we're embarking on a journey not just through space, but through the ambitious, sometimes controversial, and utterly captivating realm of field propulsion. This isn't about the raw, explosive power of chemical rockets, but about a more elegant, perhaps even mystical, interaction with the universe around us. Imagine a future where spacecraft don't carry tons of propellant, but instead become one with their environment, drawing energy and momentum from the cosmos itself. It's a concept that pushes the boundaries of engineering, challenges our understanding of physics, and promises a future of truly boundless exploration. Our story begins with the fundamental limitations of what we know. The mighty rocket, an icon of human ingenuity, operates on a principle as old as Newton himself. For every action, there's an equal and opposite reaction. To move forward, a rocket must expel mass backward. It's a remarkably effective system, one that has carried us to the moon and sent probes to the far reaches of our solar system. But it comes with a formidable cost. Every ounce of fuel, every pound of propellant, must be carried on board. This tyranny of the rocket equation means that the vast majority of a rocket's launch mass is, in fact, fuel. To send a small payload to Mars, we need a colossal amount of propellant, limiting our speed, our range, and ultimately, our dreams. This is where the allure of propellantless flight enters the picture. The idea is simple, yet revolutionary. What if we could generate thrust without expelling onboard mass? What if our spacecraft could simply push off something external, something already out there in the vastness of space? This fundamental shift in thinking is the core of field propulsion. When we speak of field propulsion, we're talking about a broad spectrum of ideas, from the already proven to the deeply theoretical. At its heart, it refers to systems where a spacecraft generates thrust by interacting with external fields or ambient media. Think of it as a thermodynamically open system, constantly exchanging momentum or energy with its surroundings. Instead of carrying all its fuel, it might harness streams of photons from the sun, or tap into the charged particles of the solar wind, or even interact with the powerful magnetic fields of planets. You might already be familiar with some of these concepts, even if you don't call them field propulsion. Solar sails, those gossamer-thin sheets reflecting sunlight to generate a gentle push, are a prime example. Electrodynamic tethers, long conductive wires interacting with planetary magnetospheres, offer another avenue. And magnetic sails, or mag sails, which would use immense magnetic fields to deflect the solar wind, are another. These are not science fiction. They are real, actively researched, and in some cases have already been demonstrated in space. But the term field propulsion also stretches to the edge of what we understand, venturing into realms where physics itself begins to bend. Here, we encounter more speculative mechanisms that delve into the profound depths of general relativity, quantum field theory, and even the enigmatic concept of zero-point energy. These ideas propose to alter effective inertia or couple directly to the non-particulate fields of space, challenging our very definitions of thrust and motion. The distinction between these approaches is critical. The open systems like solar sails and tethers are thermodynamically sound. They push off something real and external, conserving momentum by transferring it to or from the surrounding environment. The momentum goes somewhere. However, there's another, more controversial category, the hypothetical reactionless drives. These are the closed systems, the ones that claim to produce net thrust without any external interaction, seemingly violating the sacred law of conservation of momentum. In the world of established physics, these are met with profound skepticism, and for good reason. The universe, in all its complexity, appears to operate under very strict rules, and conservation of momentum is one of its most fundamental. Yet, the dream persists. The allure of entirely eliminating onboard propellant and the immense cost, mass, and weight associated with it continues to motivate extraordinary exploratory work. This isn't just a fringe concept. It's a topic that has attracted the attention of national space agencies, academic research groups, and even industry organizations. NASA's former breakthrough propulsion physics program, for instance, was specifically dedicated to investigating these propellantless or externally powered alternatives to conventional rockets. It's a testament to humanity's relentless drive to innovate, to look beyond the known, and to chase even the faintest whispers of what might be possible. So, let's dive deeper into this fundamental definition. Field propulsion, in its broadest sense, is about systems where thrust doesn't come from the sustained expulsion of onboard reaction mass or the burning of solid chemical fuels. Instead, it's about a dance with external fields and interaction with the cosmic medium. Solar sails, for example, gracefully harness the radiation pressure from sunlight, converting those tiny photon impulses into continuous acceleration. The Japan Aerospace Exploration Agency's ICAROS mission successfully demonstrated this concept, showcasing the elegance of photon-driven flight. Magnetic sails, on the other hand, envision deploying vast magnetic fields to interact with the solar wind, that supersonic stream of charged particles constantly emanating from our sun, allowing the spacecraft to effectively push off it. But the definition, as with all evolving scientific concepts, can narrow. Some researchers focus on experimental electromagnetic propulsion mechanisms, such as electrohydrodynamics, or EHD, and magnetohydrodynamics, MHD, which manipulate electrically charged fluids or plasmas. And then, there are those audacious proposals that invoke the deepest theories of physics, general relativity, quantum field theory, or zero-point energy, as potential pathways to modify inertia or directly couple with the structured quantum vacuum itself. The underlying principle, regardless of the specific mechanism, is the same. Motion results from environmental coupling rather than from carrying and ejecting propellant. Imagine a ship at sea. A conventional rocket is like a speedboat burning fuel. A field propulsion system, in contrast, is more like a sailboat, drawing its motive force from the wind, or a sub using magnetic forces to push off the water around it. By interacting with these external reservoirs, be it the photon field of sunlight, the charged particles of the solar wind, or the magnetic fields of planetary environments, a spacecraft could, in principle, convert ambient energy or momentum into acceleration. However, the shadow of skepticism still looms large over those aforementioned reactionless drives. These are systems presented as closed, claiming to generate thrust without any identifiable external interaction. They lack a counter-momentum reservoir, something to push off from, which puts them in direct conflict with the conservation of momentum, a bedrock principle of physics. Scientific literature, almost universally, regards such claims as violating myriad physical laws. It's a critical distinction to make. Open systems that exchange momentum with the environment are theoretically sound, even if technically challenging. Closed systems that claim to generate thrust from nothing remain firmly in the realm of speculation, requiring physics far beyond our current understanding to even begin to explain. Despite these theoretical hurdles and the technical immaturity of many field propulsion concepts, research continues. The potential benefits are simply too vast to ignore. Imagine spacecraft that don't need refueling, that can accelerate continuously over vast distances, drastically reducing transit times to other stars. Such possibilities, even if decades or centuries away, inspire a persistent quest for breakthrough physics. Programs like NASA's Breakthrough Propulsion Physics didn't just focus on the engineering. They directly challenged the fundamental physics, asking whether propellantless propulsion could be made consistent with conservation laws, and if momentum exchange with ambient plasmas or fields could genuinely substitute for mass ejection. This brings us to a crucial concept: open versus closed systems. This distinction is fundamental to understanding the viability of any propulsion concept. Open systems, by their very nature, comply with the conservation of momentum. They transfer momentum to or from the surrounding environment. Consider an MHD drive, which accelerates conductive fluids using electromagnetic fields to create thrust. The Lorentz force generates that thrust, and momentum is conserved through the interaction with the external medium, be it interplanetary plasma or the solar wind. The momentum isn't magically created, it's exchanged. Reactionless drives, on the other hand, are the hypothetical closed systems that claim to produce thrust without exchanging momentum with an external entity. This is where they run afoul of the conservation of momentum, a principle so fundamental it's implicit in the work of Newton and Galileo, and explicitly arises from the spatial translation symmetry of the laws of physics, as described by Noether's theorem. Any propulsion system that purports to generate net thrust in a closed system without external interaction challenges this principle. To be viable, it would likely require physics beyond the Standard Model, a truly revolutionary understanding of how the universe works. The practicality of any open, field-coupled concept hinges on the strength of its coupling to the surrounding environment. For instance, momentum exchange with the solar wind or a magnetosphere scales with local plasma density, magnetic field magnitude, and the efficiency of wave or field interaction. In weak or highly variable environments, the thrust and control authority are correspondingly limited. This stands in stark contrast to classical chemical and conventional electric rockets, whose performance is primarily governed by the onboard propellant and its energy. Their limits are about achievable exhaust velocity and energy density. Hypothetical field propulsion systems, while promising propellantless travel, face a different set of constraints. Their dependence on external media and the absolute necessity of complying with conservation laws. The conservation laws are the ultimate arbiters of what is physically viable. Momentum is always conserved in experiments, making it a non-negotiable requirement for any propulsion system. This principle, stemming from spatial translation symmetry, dictates that for any open system to work, it must exchange momentum with an external medium, photons, plasma, or magnetic fields. Claims of reactionless closed systems simply clash with this immutable framework. In any propulsion technology, some form of energy exchange is required. To generate a forward thrust force, F, there must be an equal and opposite change in momentum. If mass is ejected, the force F is related to the power P required by F equals P/V, where V is the ejection velocity. If mass-free energy, like photons, is ejected, then F equals P/C, where C is the speed of light. For a pure photon rocket, the efficiency is incredibly low, meaning you need immense power for even a tiny thrust. However, if a local field can interact with a large-scale field of the same type residing in space, the efficiency can dramatically improve, especially if the ejection velocity of that interaction is much less than the speed of light. This is the very essence of field effect propulsion, tapping into those ambient fields. A practical implication of this is that devices that exchange momentum with slow external media, such as plasma or magnetic fields, can, in principle, achieve higher thrust per unit input power than pure photon emission. But this comes with a caveat. It only works in environments that provide sufficient coupling strength. In the empty void of interstellar space, far from stars and planetary magnetospheres, such interactions might be too weak to be useful, driving the need for more exotic and currently theoretical approaches. The history of field propulsion research is a fascinating chronicle of human ambition and scientific evolution. It really took off in the 1960s as chemical rockets began to approach their theoretical limits. Engineers and scientists, tasked with pushing the boundaries of space travel, started looking for alternatives. Early contractor reports for the Air Force and NASA began categorizing these exotic propulsion schemes, grouping them under headings like thermal, field, and photon propulsion. This allowed them to compare vastly different concepts within a common framework. In these early taxonomies, field broadly referred to approaches that could exchange momentum or energy with external reservoirs like plasmas, magnetic fields, or directed energy sources. These were seen as long-range prospects, not near-term flight systems, but the terminology of field propulsion took root. Through the 1960s to the 1990s, electric and electromagnetic propulsion systems steadily matured. While some systems saw limited operational flights, they still largely relied on carrying propellant, despite their strong field components. The more speculative end of the spectrum, concepts aiming to push off against the environment without carrying any reaction mass, remained firmly in the research phase. Reports from the Air Force Rocket Propulsion Laboratory and the Jet Propulsion Laboratory in the 1970s and 80s formalized this division, reiterating the categories and emphasizing infinite specific impulse systems. These were the ones that would obtain both working fluid and energy from the ambient environment, promising exceptional performance potential. The hope was that breakthroughs in lasers and superconductors might re-energize earlier, discarded concepts like laser propulsion or ramjets. By the late 1990s, this classification system was wholeheartedly embraced by NASA's Breakthrough Propulsion Physics program. This program explicitly wrestled with the fundamental questions. Could propellantless propulsion be made consistent with conservation laws? Could momentum exchange with ambient plasmas or fields truly substitute for mass ejection? Subsequent studies by the NASA Institute for Advanced Concepts, or NJC, continued this inquiry, exploring ideas like all-vane wave coupling and other plasma interactions to generate quasi-propellantless thrust. Across all these efforts, researchers at the physics frontier acknowledged the conceptual appeal of field propulsion, but remained acutely aware of the unresolved consistency issues that arose whenever a clear external momentum channel couldn't be definitively identified. The terminology itself can be a source of confusion, as different surveys and program documents use field or field-adjacent language in varying ways. Some group advanced options under thermal, field, and photon propulsion, with field covering externally powered and field interactive concepts beyond conventional rocketry. Others, focusing on electromagnetic propulsion, categorize plasma or ion engines as electric propulsion. While these do employ strong electromagnetic fields, they still expel reaction mass. The true physics frontier programs define an aspirational target, propulsion that requires no propellant mass. This is where the studies of momentum exchange via ambient fields and other non-chemical pathways truly reside. NASA's Breakthrough Propulsion Physics effort, established in 1996, set explicit research goals. Propulsion with no propellant mass, achieving the maximum physically possible transit speeds, and discovering breakthrough energy methods to power such devices. This program framed the entire field propulsion question in terms of fundamental physics limits and testable claims. The NIAC, in parallel, funded studies on using ambient plasmas and magnetic fields, like the solar wind and planetary magnetospheres, to generate thrust without expelling onboard propellant, including those fascinating all-vane wave coupling concepts. These efforts were explicitly designed to separate testable physics from non-viable claims, using these ambitious goals to scope out candidate studies across sails, tethers, and the more speculative field interaction ideas. In a 1983 NASA contractor survey on advanced beamed energy and field propulsion concepts, the argument was made that future missions would demand propulsion capabilities far exceeding chemical rockets. It examined systems where power is transmitted to the vehicle via lasers, microwaves, or particle beams, effectively decoupling the onboard energy source from thrust production. This report organized prospects into those familiar thermal, field, and photon classes, identifying critical enabling technologies like higher current superconductors or even hypothetical room temperature superconductors as potential gateways to unlock advanced field interactive designs. It also noted the historical funding swings for advanced propulsion, from surges in the 60s and early 70s to sharp reductions after 1975, underscoring the cyclical nature of ambitious scientific endeavors. The report suggested that demonstrating plausible, efficient advanced propulsion systems might be the catalyst for the next wave of major space activities, serving as the trigger rather than merely the outcome of such expansion. Beamed energy propulsion, for instance, eliminates the need for onboard energy sources by transmitting power from remote stations. This could lead to high specific impulse with relatively high thrust-to-weight ratios. Theoretical development in this area includes mechanisms for transferring momentum via electromagnetic coupling, or even interacting with the physical structure of the vacuum itself, a line of reasoning that closely parallels the most speculative field propulsion concepts. Some approaches even explore using atmospheric or ambient materials as a virtual reaction mass or interaction medium, pushing far beyond the limitations of traditional mass ejection propulsion. This includes advanced electrostatic and MHD-based concepts that could leverage charged particle interactions with atmospheric fields to produce directed motion. A 1972 Air Force Rocket Propulsion Laboratory study, aiming to explore transitions beyond chemical propulsion, categorized advanced propulsion into thermal, field, and photon domains. It emphasized a return to the unrestricted creativity that characterized propulsion research in the late 1950s and early 1960s. Among its key conclusions, the AFRPL report highlighted that more intensive energy sources, like nuclear power, offered performance improvements up to 5 orders of magnitude greater than chemical sources. It proposed that researchers prioritize infinite specific impulse systems that could obtain both working fluid and energy from the ambient environment, offering truly exceptional performance potential. For field propulsion, specific technological breakthroughs like higher current density superconductors, metallic hydrogen, or room temperature superconductors were identified as potentially enabling innovations. The study argued that improvements in technologies like high-power lasers or new energy transfer methods could breathe new life into previously discarded ideas, including laser propulsion and those infinite ISP ramjets. The vision of beaming energy wasn't limited to within our solar system. In 1984, the physicist Robert Forward extended these beamed sail studies to the interstellar scale, suggesting that phase solar system lasers could impart sustained acceleration to ultralight sails across astronomical distances. He calculated that such a system might accelerate a probe to roughly 11% the speed of light, reaching Alpha Centauri in about 4 decades, bringing the timescale of an interstellar flyby within a human lifetime. Imagine that, a journey to another star system, not in millennia, but in a single human generation, powered by beams of light from our home star. The world of field propulsion is vast, ambitious, and deeply rooted in the fundamental laws of the universe, even as it seeks to stretch them. From the elegant simplicity of solar sails to the mind-bending concepts of manipulating spacetime itself, the human quest to master cosmic travel continues. But as we've seen, every dream must contend with the unyielding realities of physics. The conservation of momentum is a formidable gatekeeper, demanding that for every push, there must be a corresponding pull. The true genius lies in finding that pull not within our limited onboard resources, but within the boundless energy of the cosmos itself. In our next segment, we'll explore some of the more proven methods of field propulsion, technologies that are already shaping the future of space travel, even if they remain in their nascent stages. We'll delve into the fascinating mechanics of these systems and uncover how they're beginning to harness the very fields that permeate our universe. In our last segment, we contemplated the inherent limits of conventional rocket propulsion, a system that, for all its revolutionary impact, remains fundamentally tethered to the finite mass of its onboard propellant. We looked out at the vastness of space and understood that to truly reach for the stars, or even to efficiently traverse our own solar system, we need to untether ourselves from this constraint. This naturally brings us to the tantalizing realm of field propulsion. Imagine, if you will, a spacecraft that doesn't carry its fuel, but instead pushes off the very fabric of the cosmos. This is the essence of field propulsion. It encompasses a fascinating array of proposed and actively researched concepts, all geared towards generating thrust by coupling a vehicle to external fields or ambient media, rather than by continuously expelling onboard propellant. Think of it as a cosmic sailor, harnessing the winds and currents of space itself. This broad definition highlights a crucial distinction. Field propulsion schemes are thermodynamically open systems. This means they are designed to exchange momentum or energy with their surroundings. They might interact with streams of photons, like a solar sail catching the sunlight, or with radiation or magnetized plasma, like a magnetic sail interacting with the solar wind, or even with planetary magnetospheres, as is the case with electrodynamic tethers. These are not merely theoretical musings. They are familiar exemplars that have been successfully demonstrated in laboratories, field tests, and even in low Earth orbit. However, it's vital to distinguish these open systems from a more speculative and indeed controversial category: hypothetical reactionless drives. These are closed systems that claim to produce net thrust without any external interaction. While alluring, they are widely regarded as violating the fundamental law of conservation of momentum and challenging the very foundations of the standard model of physics. For our journey today, we will focus on the proven and the promising, the concepts that dance within the bounds of established scientific principles. Within the landscape of aerospace engineering research, the label field propulsion spans both established and truly cutting-edge approaches. We're talking about methods that effectively push off external reservoirs. Photonic pressure from the sun, which is the driving force behind solar sails. Charged particle streams, such as the solar wind, which are utilized by magnetic sails and their related magnetic structures. And, of course, interactions with planetary magnetospheres and ionospheric environments, the domain of electrodynamic tethers. In a more nuanced usage, the term also extends to efforts that aim to engineer field matter coupling using electromagnetic propulsion. This includes fascinating concepts like electrohydrodynamics and magnetohydrodynamics. And then, at the far edge of theoretical physics, it even covers speculative mechanisms that draw on general relativity, quantum field theory, or zero-point energy ideas, all with the audacious goal of altering effective inertia or coupling directly to the non-particulate fields of space itself. Let's be clear. While several elements of field-coupled propulsion have been successfully demonstrated, no field propulsion method has yet been fully validated as a practical primary propulsion system for large-scale interplanetary or interstellar missions. Currently, their known applications are largely limited to orbital operations. Even so, the sheer prospect of exchanging momentum with external energy or matter reservoirs, thereby drastically reducing the carried rocket propellant, and thus the colossal cost, mass, and weight associated with it, continues to motivate an incredible amount of exploratory work. This topic remains a vibrant area of research in programs such as NASA's former Breakthrough Propulsion Physics program, as well as in ongoing studies by national space agencies, academic research groups, and industry organizations, all investigating propellantless or externally powered alternatives to the conventional rocket engines and electric propulsion systems that have defined space travel for decades. So, let's dive deeper into the definition. The broad definition of field propulsion, as we've established, refers to propulsion systems in which thrust arises from interactions with external fields or ambient media, rather than from the sustained expulsion of onboard reaction mass or reliance on solid chemical fuels. In this framework, the familiar exemplars include solar sails, magnetic sails, and electrodynamic tethers. These systems couple with external photon, plasma, or magnetic fields instead of expelling onboard propellant. Some field propulsion reviews explicitly note that open systems exchange momentum or energy with external media, and that proposals of closed-system, reactionless dry propulsion are viewed with deep skepticism because they fundamentally conflict with the conservation of momentum. This stands in stark contrast to conventional rockets, which achieve motion by the powerful expulsion of mass. Most commonly, this is the combustion output from chemical propellants, generating thrust via Newton's third law, the familiar spectacle of an explosive flame and smoke beneath a rocket at launch. This method has dominated aerospace propulsion since the advent of gunpowder in ancient warfare, initial rocketry concepts in the 14th century, and the internal combustion engine for aviation in the 20th century. A venerable lineage, certainly, but one that is pushing its fundamental boundaries. Field propulsion is not a singular technology, but rather a vast spectrum of approaches. This spectrum ranges from relatively mature concepts that have been thoroughly tested in flight to highly speculative theoretical constructs. The broader definitions often include systems like solar sails, exemplified by the Japan Aerospace Exploration Agency's ICAROS mission. ICAROS successfully demonstrated propulsion by harnessing the subtle, yet persistent, radiation pressure from sunlight. In a similar vein, magnetic sail concepts, proposed by visionaries like Dana Andrews and Robert Zubrin, envision the use of vast magnetic fields to couple with the solar wind, thereby transferring its momentum to a spacecraft. However, narrower definitions sometimes home in on experimental electromagnetic propulsion mechanisms. These include electrohydrodynamics, or EHD, and magnetohydrodynamics, MHD. Even more speculatively, they consider proposals that invoke general relativity, quantum field theory, or zero-point energy as potential pathways to modify inertia or couple directly to the structured quantum vacuum, a concept that pushes the very boundaries of our understanding of reality. The category of various types of field propulsion concepts investigates mechanisms where motion results from environmental coupling, rather than from carrying and ejecting propellant. Examples include systems that attempt to draw on the photon field of sunlight, the charged particles of the solar wind, or the magnetic fields of planetary environments. By interacting with such external reservoirs, a spacecraft could, in principle, push off the surrounding medium, converting environmental energy or momentum into acceleration. Meanwhile, those aforementioned hypothetical reactionless drives and related unproven constructs occupy a more controversial space. They are framed as closed systems that claim to generate thrust without any identifiable external interaction, because they conspicuously lack a countermomentum reservoir, that is, a reaction mass or something tangible to push off from. They are widely regarded in the scientific literature as violating a myriad of fundamental physical laws. It's important to reiterate, although various terrestrial and laboratory-scale systems have provided partial demonstrations, no field propulsion method has yet been validated as a reliable primary propulsion system for practical spaceflight. Nonetheless, the topic continues to attract intense research attention, both because of the profound theoretical challenges it raises and because of the truly transformative potential benefits, if even one class of these systems could be made viable. Exploratory programs have included the pioneering Breakthrough Propulsion Physics program at NASA, as well as ongoing studies conducted under the auspices of other national space agencies, academic laboratories, space-related organizations, and private industry. Concurrently, Options related to non-rocket space launch are also under active investigation, all driven by the same profound desire to escape the tyranny of the rocket equation. This brings us to a critical distinction: open versus closed systems. Open systems, by their very nature, comply with the fundamental conservation of momentum by transferring it to or from the surrounding environment. For instance, magnetohydrodynamic, or MHD, drives accelerate conductive fluids using electromagnetic fields, resulting in thrust through the Lorentz force. Momentum is conserved here via interaction with external media, such as the interplanetary or interstellar media or the solar wind. This is entirely consistent with our understanding of physics. In stark contrast, reactionless drives are hypothetical closed systems that claim to produce thrust without exchanging momentum with an external entity. In doing so, they would directly violate the conservation of momentum. As such, they are widely regarded as inconsistent with established scientific principles. This conservation law is not just an arbitrary rule. It is implicitly present in the published work of scientific giants like Newton and Galileo. More fundamentally, it arises from the spatial translation symmetry of the laws of physics, a deep principle beautifully articulated by Noether's theorem. Any propulsion system that purports to generate net thrust in a closed system without external interaction fundamentally challenges this principle. Under the standard model of physics, such a system is considered physically untenable. To be viable, it would likely require physics beyond the standard model, a profound shift in our understanding of the universe. In practical terms, the viability of any open field-coupled concept hinges entirely on its coupling strength to the surrounding environment. For example, momentum exchange with the solar wind or a magnetosphere scales with the local plasma density, the magnetic field magnitude, and the efficiency of the wave or field interaction. In weak or highly variable environments, the thrust and control authority are correspondingly limited. These constraints stand in sharp contrast to classical chemical and conventional electric rockets, whose performance is primarily governed by the onboard propellant and its energy. This reflects fundamental engineering limits on achievable exhaust velocity and energy density. Hypothetical field propulsion systems, however, are framed in the literature as propellantless, yet they inevitably encounter a dependence on external media and face unresolved consistency challenges with conservation laws. Let's delve a little deeper into these conservation laws, as they form the bedrock of what is physically viable. Building on this distinction between open and closed systems, conservation laws frame the absolute boundary conditions for what types of propulsion are physically viable and which remain speculative or, frankly, untenable. The conservation of momentum is a fundamental, non-negotiable requirement of propulsion systems, because in every single experiment ever conducted, momentum is always conserved. This conservation of momentum is a fundamental principle, arising directly from spatial translation symmetry. Reviews of field propulsion concepts consistently emphasize that any open system must exchange momentum with an external medium, be it photons, plasma, or magnetic fields. Conversely, claims of closed-system, reactionless propulsion fundamentally conflict with this immutable framework. In each of the propulsion technologies we consider, some form of energy exchange is required, with momentum directed backward at the speed of light, c, or some lesser velocity, v, to balance the forward change of momentum. In the absence of interaction with an external field, the power P that is required to create a thrust force F is given by the elegant equation, F equals P divided by V, when mass is ejected, or F equals P divided by C, if mass-free energy is ejected. For a pure photon rocket, the efficiency is simply too small to be competitive for most practical applications. Other technologies may have better efficiency if the ejection velocity is less than the speed of light, or, critically, if a local field can interact with another large-scale field of the same type residing in space, which is precisely the intent of field effect propulsion. A practical implication of this is that devices which exchange momentum with slow external media, such as plasma or magnetic fields, can, in principle, achieve a higher thrust per unit input power than pure photon emission. This is because for photon emission, the v in our equation becomes c, the speed of light, which is an incredibly large denominator, making the resulting thrust small for a given power input. However, this advantage comes with a caveat. It only applies within environments that provide sufficient coupling strength. In the vacuum of deep space, far from any plasma or magnetic fields, such systems would struggle. The discussion of field propulsion in aerospace literature has rarely been isolated to a single technology. Instead, it has appeared most often in broad surveys and strategic roadmaps, attempting to organize these non-chemical propulsion concepts into recurring categories. Beginning in the 1960s, a pivotal time when chemical rockets were rapidly approaching their theoretical limits, contractor reports for the Air Force and NASA began grouping alternatives under three distinct headings: thermal, field, and photon. This allowed exotic schemes to be compared within a common, coherent framework. Within this taxonomy, field broadly referred to approaches that might exchange momentum or energy with external reservoirs, such as plasmas, magnetic fields, or directed energy sources, and therefore contrasted sharply with both conventional rockets and nuclear thermal designs. These early surveys tended to treat such concepts as long-range prospects, rather than near-term flight systems, but they successfully kept the terminology of field propulsion alive through successive planning cycles. During the 1960s through the 1990s, electric and electromagnetic propulsion technologies matured experimentally. Some systems even began flying in limited operational roles, though it's important to note that even these continued to rely on propellant, despite their strong field components. By contrast, the more speculative end of the spectrum, concepts that sought to push off against the environment without carrying any reaction mass, remained firmly in the research phase. A 1972 Air Force Rocket Propulsion Laboratory report, followed by Jet Propulsion Laboratory studies in 1975 and 1982, formalized this division by publishing roadmaps that, once again, divided advanced concepts into thermal, field, and photon classes. These reports emphasized infinite specific impulse systems, those that would obtain both energy and working fluid from the ambient environment, and suggested that new advances in lasers and superconductors might breathe new life into earlier discarded concepts such as laser propulsion or ramjets. By the late 1990s, this style of classification had been enthusiastically adopted by NASA's Breakthrough Propulsion Physics program. This visionary program explicitly posed the fundamental question: could propellantless propulsion be made consistent with conservation laws? And further, could momentum exchange with ambient plasmas or fields truly substitute for mass ejection? Later studies by the NASA Innovative Advanced Concepts, or NJC, program continued in this vein, meticulously examining whether all vane wave coupling or other sophisticated plasma interactions might provide quasi-propellantless thrust. Across all these rigorous efforts, surveys at the physics frontier acknowledge the profound conceptual appeal of field propulsion, but also consistently stressed the unresolved consistency issues that inevitably arise when no clear external momentum channel can be unequivocally identified. Let's clarify the scope and terminology as used in various sources. Published technical surveys and program documents employ field or field-adjacent language in different ways. Contractor studies for NASA, for instance, grouped advanced options under headings such as thermal propulsion, field propulsion, and photon propulsion, with field serving as a broad umbrella for externally powered and field interactive concepts that went beyond conventional rocketry. However, surveys focusing specifically on electromagnetic propulsion often categorize plasma and ion engines, including pulsed plasma, magnetoplasmodynamic, and pulsed inductive thrusters, as electric propulsion. While these devices certainly employ strong electromagnetic fields, they fundamentally still expel reaction mass. In contrast, Physics Frontier program statements define an aspirational target class as propulsion that requires no propellant mass, directly motivating studies of momentum exchange via ambient fields and other truly non-chemical pathways. programmatic efforts have been pivotal in advancing this field. NASA's Breakthrough Propulsion Physics, or BPP, effort, established in 1996, set audacious research goals. These explicitly included propulsion that requires no propellant mass, the pursuit of the maximum physically possible transit speeds, and the development of breakthrough energy methods to power such devices. This program brilliantly framed the field propulsion question in terms of fundamental physics limits and rigorously testable claims. Separately, the NASA Institute for Advanced Concepts, NIAC, funded crucial studies on using ambient plasmas and magnetic fields, such as the solar wind and planetary magnetospheres, to generate thrust without expelling onboard propellant. This included cutting-edge all-vane wave coupling concepts, framed explicitly as a way to separate genuinely testable physics from non-viable claims. The BPP articulated three headline goals: propulsion with no propellant mass, maximum physically possible transit speeds, and breakthrough energy sources. These ambitious goals then served to scope candidates' studies across solar sails, electrodynamic tethers, and more speculative field interaction ideas. A particularly insightful NASA contractor survey from 1983, titled Advanced Beamed Energy and Field Propulsion Concepts, written by Marabo, argued compellingly that emerging missions would require propulsion capabilities far exceeding those of chemical rockets. It meticulously examined systems where power is transmitted to the vehicle via lasers, microwaves, or particle beams, thereby effectively decoupling onboard energy from thrust production. The report organized these prospects into thermal, field, and photon classes and identified key enabling technologies, such as higher current superconductors and the potential for room temperature superconductors, as critical gates to developing viable field interactive designs. It thoughtfully noted historic funding swings and prior AFRPL/JPL surveys, situating field concepts within the long-running tradition of advanced propulsion road mapping, rather than as near-term flight systems. The report suggested that while nuclear electric and solar electric propulsion systems were advancing and might see application before 1990, they would still be insufficient for the grand vision of large-scale industrial use of lunar or asteroidal materials. Marabo concluded that demonstrating plausible, efficient advanced propulsion systems might well catalyze the next wave of major space activities, potentially serving as the trigger, rather than merely the outcome, of such an expansion. These advanced propulsion systems, it was argued, could overcome the inherent limitations of chemical rockets by accessing more energetic physical principles, particularly those involving directed energy and field interactions. Beamed energy propulsion concepts, for example, eliminate the need for heavy onboard energy sources by transmitting power from remote stations using lasers, microwaves, or particle beams to induce thrust remotely. Such systems decouple the vehicle from traditional propellant constraints and open up the tantalizing possibility of achieving high specific impulse with relatively high thrust-to-weight ratios. Theoretical development in this area includes mechanisms for transferring momentum via electromagnetic coupling or by interacting directly with the physical structure of the vacuum itself, a line of reasoning that closely parallels other field propulsion concepts. Some approaches even explore the utilization of atmospheric or ambient materials as a virtual reaction mass or interaction medium, pushing far beyond the limitations of traditional mass ejection propulsion. Proposals also include advanced electrostatic and MHD-based concepts that could leverage charge-particle interactions with atmospheric fields to produce directed motion. The funding for advanced propulsion research saw major swings from the 1960s to the early 1980s. There were initial surges of investment during the 1960s and early 1970s, followed by sharp reductions after 1975. Notable reports on advanced propulsion during this challenging funding trough include studies by the Air Force Rocket Propulsion Laboratory in 1972 and the Jet Propulsion Laboratory in 1975 and 1982. The 1972 Air Force Rocket Propulsion Laboratory, or AFRPL, study was specifically conducted to explore transitions beyond chemical propulsion and to stimulate the development of more advanced, high-performance systems by the end of the 20th century. The AFRPL report categorized advanced propulsion into three domains: thermal propulsion, field propulsion, and photon propulsion, with each rigorously evaluated for its performance potential. The study powerfully emphasized a return to the unrestricted creativity and free thinking that had so characterized propulsion research in the late 1950s and early 1960s. Among its primary conclusions, the AFRPL report noted that more intensive energy sources, such as nuclear power, offer performance improvements up to 5 orders of magnitude greater than chemical sources. It boldly proposed that propulsion researchers should prioritize infinite specific impulse systems, those that obtain both working fluid and energy from the ambient environment, thereby offering truly exceptional performance potential. For field propulsion, specific technological breakthroughs were identified as potentially enabling innovations, such as higher current density superconductors, metallic hydrogen, or even room temperature superconductors. The study argued that improvements in technologies like high-power lasers or new energy transfer methods could revitalize previously discarded propulsion ideas, including laser propulsion and those elusive infinite ISP ramjets. Taking this concept even further, in 1984, the physicist Robert Forward extended beam sail studies to the interstellar scale. He suggested that phase solar system lasers could impart sustained acceleration to ultralight sails across astronomical distances. He calculated that such a system might accelerate a probe to approximately 11% the speed of light, potentially reaching Alpha Centauri, our nearest star system, in about 4 decades, bringing the timescale of an interstellar flyby tantalizingly within a single human lifetime. A 1993 NASA review by Myers, focusing on electromagnetic propulsion, identified 3 main types of electromagnetic propulsion systems: pulse plasma thrusters, or PPTs, magneto-plasmodynamic thrusters, or MPD, and pulsed inductive thrusters, or PITs. PPTs had already flown, primarily for attitude control and drag makeup on satellites. MPD devices had a space heritage in experimental regimes, and PITs sought to reduce electrode erosion limits by employing inductive coupling. The review highlighted the benefits of these systems: high specific impulse, precise impulse bits, and robustness, alongside their unresolved issues, such as efficiency, cathode wear, and challenges with spacecraft power and integration. It presented these as sophisticated electric propulsion architectures that, importantly, still accelerate propellant, even when strong fields are central to their operation. Pulse plasma thrusters, or PPTs, represent the earliest class of electromagnetic propulsion systems to achieve operational deployment in space. Developed in the 1960s, these thrusters generate thrust by ablating a solid propellant with an arc discharge and then accelerating the resulting plasma via Lorentz forces. Unlike later concepts relying on inductive or steady-state operation, PPTs utilize compact, low-power, pulse configurations, making them suitable for satellite positioning and drag compensation. The Soviet Zond 2 Mars mission in 1964 marked the very first planetary use of electric propulsion, followed by successive U.S. deployments that culminated in the Nova satellite series. PPTs remain relevant today for low-mass spacecraft requiring precise impulse bits, though scaling them to higher power levels has presented persistent technical challenges. Magneto-plasmodynamic thrusters, or MPTs, constitute another major class of electromagnetic propulsion systems that have been investigated for both quasi-steady and steady-state spaceflight applications. Operating through the Lorentz force, generated by the interaction of discharge currents with self-induced or externally applied magnetic fields, MPD thrusters were among the first electric propulsion devices to actually fly in space. Initial experimental campaigns explored both self-field and applied field configurations, with development advancing through international programs aimed at supporting high-power planetary missions. While technological challenges remain, including efficiency optimization and, notably, cathode erosion, MPD thrusters continue to serve as a key pathway towards scalable, high-thrust, long-duration propulsion architectures. Pulsed inductive thrusters, or PITs, are a form of electromagnetic propulsion specifically developed to overcome the erosion and lifetime limitations of electrode-based systems. By inducing plasma currents through time-varying magnetic fields, PITs accelerate neutral propellants without requiring any physical contact between conductors and the plasma. The concept originated in the late 1960s and has evolved through successive experimental designs, all focused on performance scaling, circuit optimization, and propellant compatibility. Although no PIT system has yet flown in space, this thruster class remains of significant interest due to its potential for high-efficiency, long-duration propulsion with minimal material degradation, particularly in missions requiring flexible propellant selection and reduced contamination risk. Returning to the physics frontier, NASA's Breakthrough Propulsion Physics, or BPP, memo from 1998 and later work by Minami and Musha in 2012 framed research questions at the very limits of physics. This included no propellant propulsion, the quest for ultimate transit speeds, and breakthrough energy production. The explicit goal was to rigorously sort physically testable ideas from those non-viable claims that strayed too far from scientific principles. Minami and Musha, in particular, surveyed a class of proposals that posit a substantial physical structure of space-time or vacuum, macroscopic in general relativity, microscopic in quantum field theory. They investigated whether asymmetries in massless fields or vacuum-medium interactions could truly yield thrust without mass expulsion. Their conclusion: such systems remain theoretical and controversial, with ongoing but inconclusive experiments and persistent consistency concerns with momentum conservation. This dual framework situates field propulsion concepts squarely at the intersection of general relativity, which treats spacetime as a dynamic geometry, and quantum field theory, where the vacuum itself hosts fluctuating fields and latent energy. Several mechanisms have been theorized to achieve such coupling, including vacuum polarization, direct space-time curvature manipulation, and asymmetrical force distributions generated by interactions with massless fields. Though none have been experimentally validated, laboratory-scale studies have sought force generation analogs, such as those related to zero-point energy fluctuations and electrogravitic interactions. However, the results have remained largely inconclusive and notoriously difficult to replicate. A central theoretical challenge for all of these concepts is their reconciliation with the conservation of momentum. Without a clearly identified external momentum exchange medium, such mechanisms would, by current understanding, violate fundamental physical laws. A 2011 NIAC Phase 1 study conducted by Gilland and Williams evaluated ambient plasma wave propulsion. This research focused specifically on momentum exchange with existing space environments, such as the solar wind and planetary magnetospheres, via waves like Alfvén modes. These, alongside solar sails and electrodynamic tethers, were considered as prime candidates for propellantless or quasi-propellantless thrust. The authors highlighted both the profound appeal of such concepts, chiefly the absence of any onboard reaction mass, and their significant limitations, including technical immaturity and shortfalls in power and sensitivity for significant maneuvering. Across all these diverse sources, conventional rocket and electric systems consistently remain the baseline for operational missions. Their performance is reliably bounded by the energy and momentum balances described in standard propulsion texts. Field-coupled approaches that genuinely exchange momentum with external photon, plasma, or magnetic reservoirs are entirely consistent with conservation laws, provided that the external medium truly provides the countermomentum. However, claims of net thrust in closed systems, without such an identifiable exchange, directly conflict with the momentum conservation framework that is so strongly emphasized in physics frontier reviews. A complementary way to frame performance is through mission energetics, rather than simply hardware categories. This shifts the emphasis from individual devices to the delicate balance between energy, mass, and external coupling. In this view, Field-coupled systems inherently trade carried propellant mass for a dependence on ambient fluxes and on the vehicle's ability to efficiently couple power into those fluxes. Solar sails, for example, scale their acceleration with the available solar irradiance and their sail area-to-mass ratio. This means that sails profoundly reward extreme aerial density reductions and incredibly precise attitude control. However, they offer very little thrust authority in deep shadow or far from the sun, where the flux drops dramatically with the square of the heliocentric distance. Magnetic or magnetospheric sail concepts similarly scale with the dynamic pressure of the impinging plasma and with the effective standoff distance of the vehicle's magnetic field structure. This leads to a design space heavily dominated by coil mass, current, and the precise control of magnetic topology in highly variable plasma conditions. Another recurring theme is the idea that open systems can essentially move the propellant problem elsewhere, into the environment itself, or even into the ground segment. Beamed energy concepts, for instance, externalize the entire power plant to a remote transmitter, while the vehicle mainly provides an absorber, a converter, and steering mechanisms. This dramatically reduces carried mass, but imposes stringent line-of-sight and infrastructure constraints, and also introduces complex beam riding guidance and safety considerations. In contrast, conventional electric propulsion systems internalize both energy conversion and propellant handling. This simplifies operations in sparse environments, but comes at the price of carrying significant reaction mass and often heavy power processing hardware. Let's be absolutely clear. Momentum conservation is the fundamental, non-negotiable boundary on all propulsion concepts. Devices that attempt to produce thrust without propellant or any other identifiable exchange of momentum are, by current understanding, not consistent with known physics. Academic reviews consistently echo this conclusion, stating unequivocally that propulsion systems which generate thrust without reaction mass or interaction with external fields are regarded as inconsistent with the present framework of physics. However, environment-coupled approaches, such as sails, tethers, or plasma wave coupling, remain very much possible if the method of external coupling is sufficiently strong and well understood. Field propulsion concepts are typically grouped into broad classes that distinguish precisely how momentum exchange is achieved and whether propellant is carried on board. In the most frequently cited taxonomy, one category encompasses environment-coupled systems that draw upon external reservoirs. This includes solar sails, which push against photon flux, magnetic or magnetospheric sails, which couple with the solar wind, and electrodynamic tethers, which interact with planetary magnetic fields. A second category covers electrically driven devices in which strong electromagnetic fields dominate the acceleration physics, but in which momentum closure still proceeds through the exhaust of a carried propellant. Representative examples here include pulsed plasma thrusters, magnetoplasmodynamic thrusters, and pulsed inductive thrusters. A further and far more speculative class invokes direct interactions with a structured vacuum or with spacetime geometry itself. These concepts propose thrust without any expulsion of mass whatsoever, an idea surveyed in the general relativity and quantum field theory literature, but one that remains entirely empirically unvalidated. Finally, some historical NASA surveys also grouped beamed energy propulsion into field or field-adjacent categories, primarily because the energy supply is external to the vehicle, with power transmitted by laser, microwave, or particle beams, rather than carried on board. This layered taxonomy reflects the systematic way that contractor reports and program reviews organized this complex subject during the late 20th century. Air Force Rocket Propulsion Laboratory and Jet Propulsion Laboratory roadmaps in the 1970s and 1980s consistently placed advanced systems into three headings: thermal, field, and photon, explicitly separating concepts that drew energy or momentum from their environments from those that remained tethered to finite onboard propellant stores. Within that scheme, field propulsion was deliberately used as a broad umbrella for externally powered or environment-coupled designs, not as an endorsement of reactionless claims. This careful usage carried into later breakthrough propulsion physics framing at NASA, where propellantless propulsion was treated as a profound research question at the very boundary of physics, rather than a mature technology. In contemporary technical reviews, it has become common practice to reserve the term field propulsion, specifically for schemes that exchange momentum with external reservoirs, as these remain entirely consistent with the conservation of momentum when an identifiable medium truly supplies the counterforce. By contrast, devices such as PPT, MPD, and pit thrusters, while undoubtedly dominated by internal electromagnetic fields, are now placed within the broader family of electropropulsion because their exhaust streams ultimately provide the reaction mass that enforces momentum balance. This careful delineation has become standard in academic surveys, serving both to clarify what is physically admissible under current theory and to rigorously distinguish between near-term electrotechnologies and the more speculative, true field-coupled approaches. Let's look at field-adjacent concepts, particularly beamed energy propulsion. Historical roadmaps also considered beamed energy propulsion field-adjacent, primarily because power is supplied from outside the vehicle, via lasers, microwaves, or particle beams, and then converted to thrust onboard, effectively decoupling energy supply from carried mass. Such schemes are not truly propellantless if they still ablate or heat onboard reaction mass, but the externalization of the power source places them conceptually very near to field concepts in advanced propulsion surveys. Beyond simple ablation or thermal boost, roadmaps have meticulously examined hybrid schemes in which a vehicle carries a small amount of working fluid that is then heated or photodesorbed by a remote beam. This allows for thrust throttling while still decoupling most of the energy supply from onboard mass. Such studies typically involve a complex trade-off between transmitter complexity and stringent pointing requirements versus vehicle mass and its thermal limits. Mirrors, rectennas, or absorber cavities in the spacecraft must be engineered to survive incredibly high power densities while maintaining impeccable optical figure or RF efficiency across vast ranges. Mission analyses in this class often treat the beaming infrastructure as reusable capital equipment, amortized across multiple flights, whereas the vehicles themselves are designed to be lightweight, short-lived stages optimized for specific acceleration corridors. Then there are electric and magnetic thrusters that, despite their advanced nature, still expel propellant. Several devices central to electromagnetic propulsion rely on strong fields, yet remain entirely conventional in the momentum sense because they accelerate carried propellant. Representative families include pulsed plasma thrusters, magnetoplasmodynamic thrusters, and pulsed inductive thrusters, each presenting distinct trade-offs in terms of lifetime, efficiency, and power scaling. As we noted, PPTs have successfully flown for attitude control and drag makeup. MPD has flight heritage in experimental regimes, and PIT remains extensively ground-tested. Within the broader electric propulsion family, these devices brilliantly illustrate how strong fields can dominate the internal acceleration physics, while momentum closure still proceeds entirely through exhaust. PPTs offer exceptionally small impulse bits and remarkably simple architectures, but at the cost of limited efficiency and erosion. MPD devices promise higher thrust densities at high power, but face persistent challenges with cathode life and plume divergence. And PIT concepts ingeniously remove electrodes via inductive coupling, while introducing their own complex design trades involving pulse power and coil standoff. In programmatic roadmaps, these technologies frequently serve as crucial baselines for comparison with truly environment-coupled concepts, anchoring expectations for power-to-thrust ratios, lifetime, and system mass at mission-relevant scales. Now let's explore some practical methods, those that, while perhaps not widely used for space propulsion yet, offer compelling examples of field propulsion principles in action. There exist proven terrestrial examples where electromagnetic fields act upon a conducting medium, such as seawater or plasma, for propulsion. This is known as magnetohydrodynamics, or MHD. MHD operates similarly to electric motors, but crucially, Rather than using moving parts or solid metal conductors, it employs fluid or plasma conductors. The EMS-1 and, more recently, the Yamato-1 are striking examples of such electromagnetic field propulsion systems, first described in 1994. There is significant potential to apply MHD to the space environment. Consider experiments like NASA's electrodynamic tether, Lorentz actuated orbits, the intriguing wingless electromagnetic air vehicle, and the magnetoplasmodynamic thruster, though it's important to remember that the latter does use propellant. A NASA Institute for Advanced Concept study in 2011 specifically evaluated ambient plasma wave propulsion, a concept in which spacecraft generate alphane waves in surrounding plasma or magnetospheric fields to exchange momentum without expelling onboard propellant. The report candidly noted that such systems are technically immature, but possess the potential to enable entirely new classes of exploration missions if fully developed. In space contexts, related field-coupled approaches include photon sails, magnetic and magnetospheric sails, and electrodynamic tethers, all of which exchange momentum with external photon, plasma, or magnetic reservoirs instead of expelling onboard propellant. Electrohydrodynamics, or EHD, is another fascinating method whereby electrically charged fluids are accelerated for propulsion and flow control. Laboratory demonstrations have included so-called ionocraft devices driven by corona discharge, which silently glide through the air. Other practical methods that could be loosely considered as field propulsion include the gravity assist trajectory, a celestial billiard shot that uses planetary gravity fields and orbital momentum to slingshot a spacecraft, solar sails and magnetic sails, which use, respectively, the radiation pressure of sunlight and the solar wind for spacecraft thrust, and aerobraking, which cleverly uses the atmosphere of a planet to change the relative velocity of a spacecraft. The last two actually involve the exchange of momentum with physical particles and are not usually strictly expressed as an interaction with fields. However, they are sometimes included as examples of field propulsion because no spacecraft propellant is explicitly required from onboard stores. The MagSail magnetic sail design is a prime example of this type of thinking. Let's delve into ambient plasma wave coupling. NIAC studies have meticulously examined using radio frequency waves, such as alphane waves, launched from a vehicle to couple with ambient plasma and magnetic fields. This interaction would transfer momentum to the environment, thereby producing propellantless thrust. The 2011 Phase 1 assessment found this approach technically immature, but potentially enabling if the significant sensitivity and power challenges can be overcome. Early theoretical sketches of plasma wave momentum exchange noted that even modest wave, particle coupling coefficients could, in principle, integrate to useful changes in velocity over long dwell times, provided the vehicle can sustain transmission and maintain a favorable geometry relative to the background magnetic field. The principal hurdles remain formidable: power generation, the antenna or coil size relative to the targeted wavelengths, and the unambiguous measurement of incredibly tiny forces in a highly variable plasma environment. NIAC assessments, therefore, wisely emphasized incremental demonstrations, first characterizing coupling in controlled plasma chambers, and then evaluating low Earth orbit opportunities near strong geomagnetic gradients, before any ambitious attempt at deep space application. Electrodynamic tethers are another compelling technology. They exchange momentum with a planetary magnetosphere and ionosphere via Lorentz forces acting on a long, current-carrying conductor. This enables drag or thrust without propellant in suitable environments, such as low Earth orbit. As open systems, they flawlessly conserve momentum by reaction with the ambient plasma and magnetic field. In operation, a conductive tether moving through a planetary magnetic field experiences emotional electromotive force. Closing the circuit through the ambient ionosphere allows current to flow, and the resulting Lorentz force can provide either drag for deorbiting or, with external power injection, thrust along specific orbital geometries. Beyond simple orbit changes, tethers can also be ingeniously used for in-situ power generation, albeit at the expense of orbital energy. However, practical systems must address significant challenges. Efficient current collection, often requiring specialized plasma contactors, preventing arcing, precise attitude control, and mitigating vulnerability to micrometeoroids or space debris. Design studies for long-lived tethers consistently converge on a handful of recurring subsystems. Robust conductors with high current capacity per unit mass. Highly efficient in-body plasma contactors for current collection and emission. Sophisticated power processing electronics to govern current and polarity. And ingenious attitude control strategies that simultaneously manage gravity gradient torques and Lorentz torques. Operationally, deorbit modes cleverly exploit drag to dissipate orbital energy, while boost modes require external power injection to drive current against the motional electromotive force, thereby converting electrical input into the mechanical energy of the orbit. Both modes must carefully manage the risk of arcing at terminators and in auroral zones, suggesting operational envelopes that, where practical, avoid known space weather hazards. Magnetic and magnetospheric sails represent another fascinating class of field propulsion. Magnetic sails, including variants such as magnetospheric plasma concepts, generate thrust by coupling a spacecraft-supported magnetic field to the solar wind, thereby transferring momentum from the ambient charge particle flow to the vehicle. Such systems are firmly included in field propulsion taxonomies because they fundamentally push against an external plasma or magnetic reservoir instead of expelling propellant. Analyses of magnetic sail concepts indicate that thrust arises from deflecting the supersonic solar wind around a spacecraft-supported magnetic field, with performance ultimately set by the standoff distance of the magnetic field and the dynamic pressure of the solar wind flow. Larger effective magnetic cross-sections increase momentum transfer, but demand incredibly lightweight, high-current coils, or cleverly plasma-inflated magnetic structures. Anticipated advantages include propellantless cruise and braking throughout the heliosphere, while significant challenges include the formidable mass of the coils, demanding cryogenic or superconducting requirements, and the precise control of magnetic topology in a highly variable plasma environment. Mission sketches using magnetic sails typically fall into two main categories: heliocentric cruises that exploit the quasi-steady solar wind for outbound acceleration and inbound braking, and planetary magnetosphere operations that use local field topology for station keeping or slow orbit changes. The common design thread across all these is maximizing the effective magnetic cross-section per unit mass. Options include high-current coils made from incredibly lightweight conductors and inflatable magnetospheres in which injected plasma maintains an extended magnetic obstacle to the flow. Control is effected by modulating current or by carefully biasing the field geometry, often at the expense of additional power and thermal management complexity. Solar sails are perhaps the most conceptually elegant and, to date, the most developed form of sail-based field propulsion. They produce continuous, low-thrust acceleration by exchanging momentum with incident photons from the sun. Because the countermomentum is supplied by the external photon field, they fall squarely under broad definitions of field-coupled propulsion, rather than relying on reaction mass ejection. As with other environment-coupled concepts, their performance is directly dependent on the available flux, in this case, solar irradiance and the sail's reflectivity, and predictably falls with increasing distance from the sun. This necessitates incredibly large, lightweight structures and exquisitely precise attitude control schemes. Sailcraft engineering couples ultralight structures to incredibly stringent pointing and thermal constraints. Square or heliogero architectures, reflective coatings, boom materials, and deployment mechanisms must all be robust enough to survive the brutal forces of launch, yet unfurl in space with minimal wrinkling or creeping over time. Once deployed, the sail must hold its attitude to within extremely tight tolerances, since thrust vectoring derives from minute changes in the sail's normal orientation relative to the sun line. Performance, therefore, evolves directly with advancements in materials science and sophisticated control algorithms. Lower aerial density directly increases acceleration, while better attitude control transforms weak, continuous thrust into precise and complex trajectory shaping. Robert Forward, in a landmark 1984 paper in the Journal of Spacecraft and Rockets, outlined a proposed method in which solar system-based laser systems in a kilometer-wide Fresnel zone lens could propel thin film sails to approximately 11% the speed of light. This, he calculated, could enable an unmanned flyby of Alpha Centauri in about 40 years. In Forward's ingenious proposal, a two-stage sail system would involve a massive ring sail reflecting laser light back onto a detached payload sail, enabling the unmanned spacecraft to rendezvous with and then break within the Alpha Centauri system. A truly visionary concept. Finally, let's return to the most profound and speculative end of the spectrum. Field propulsion based on the physical structure of space itself. Minami and Musha frame field propulsion at the physics frontier as an interaction with a substantial physical structure of space. This draws on general relativity at macroscopic scales and quantum field theory at microscopic scales. Their conclusion is a powerful one, that future engineering technologies for space travel will most likely require some form of field propulsion to excite properties of localized regions in space. Surveyed mechanisms include vacuum polarization, engineered spacetime curvature, and zero-point field interactions. Crucially, none of these have been experimentally validated, and all face unresolved consistency issues with momentum conservation. This concept is fundamentally based on general relativity theory, for which the idea that space has a physical structure can be proposed. The macroscopic structure is described by general relativity theory, and the microscopic structure by quantum field theory. The audacious idea here is to deform space around the spacecraft. By deforming the space, it might be possible to create a region with higher pressure behind the spacecraft than before it. Due to this engineered pressure gradient, a force would be exerted on the spacecraft, which in turn creates thrust for propulsion. However, due to the purely theoretical nature of this propulsion concept, it is incredibly difficult to determine the precise amount of thrust and a maximum velocity that could potentially be achieved. Minami and Musha thoughtfully distinguish between two main field propulsion concepts in this realm, one framed in terms of general relativity and one in terms of quantum field theory. In the general relativistic field propulsion system, space is considered to be an elastic field, similar to rubber. This means that space itself can be treated as an infinite elastic body. If spacetime curves, a normal inward surface stress is generated, which effectively serves as a pressure field. By creating a great number of these curved surfaces behind the spacecraft, it might be possible to achieve a unidirectional surface force, which could then be used for the acceleration of the spacecraft. For the quantum field theoretical propulsion system, it is assumed, as stated by quantum field theory and quantum electrodynamics, that the quantum vacuum consists of a zero-radiating electromagnetic field in a non-radiating mode and at a zero-point energy state, the lowest possible energy state. It is also theorized that matter is composed of elementary primary charged entities, called partons, which are bound together as elementary oscillators. By applying an electromagnetic zero-point field, a Lorentz force is applied to these partons. Using this effect on a dielectric material could potentially affect the inertia of the mass, and, in that way, create an acceleration of the material without creating stress or strain inside the material itself. A profound concept, indeed, but one that currently resides firmly in the realm of theoretical physics and requires monumental breakthroughs to even begin to test. So, as we continue to gaze at the stars, the dream of harnessing the cosmos for propulsion is not merely a fantasy. It is a vibrant, active field of scientific inquiry, stretching from the tangible reality of solar sails to the deepest mysteries of spacetime itself. The path is long and fraught with challenges, but the promise of a truly propellantless future, one where we are truly free to explore, continues to beckon. The universe, in its boundless complexity, whispers to us of secrets far grander than our everyday understanding. We've journeyed through the tangible, through the rockets that defy gravity with sheer brute force, and the field propulsion systems that delicately push off the cosmos itself. But now, we stand at the precipice of an even deeper mystery, a frontier where the very fabric of reality becomes our potential pathway to the stars. This is the realm of bending space-time and tapping the vacuum, an ultimate frontier in our quest for movement without propellant, a quest to fundamentally alter our relationship with the universe. It's here that the concepts become less about pushing off something in space and more about pushing with space itself. Imagine, if you will, that space is not merely an empty void, but a dynamic, elastic medium, a cosmic ocean with hidden currents and profound depths. This isn't a poetic metaphor. It's a concept rooted in the most profound theories of modern physics, general relativity and quantum field theory. General relativity, forged by the genius of Einstein, teaches us that space-time is a pliable, four-dimensional tapestry, capable of being warped and curved by mass and energy. Quantum field theory, on the other hand, delves into the microscopic world, suggesting that even the emptiest vacuum is teeming with fluctuating fields and latent energy, a quantum foam of incessant activity. At this frontier, the grand ambition is to somehow interact directly with this substantial physical structure of space, to excite its properties in localized regions, to create asymmetries, or even to deform it in such a way that it pushes our spacecraft forward. It's a breathtaking idea, one that posits propulsion without the expulsion of a single atom of reaction mass. Consider the notion of deforming space around a spacecraft. If we could somehow create a region of higher pressure behind our vessel than in front of it, a gradient of space-time itself, then the craft would be propelled forward, much like a boat in a current. This isn't about pushing against a physical substance. It's about leveraging the intrinsic properties of space-time, treating it as an infinite elastic body. The curves and warps we observe at astronomical scales, such as those around massive stars and black holes, generate a normal inward surface stress, a pressure field. The theoretical challenge lies in engineering these curves, these microscopic undulations, in a controlled and directed manner to create a unidirectional force for acceleration. Then there's the even more enigmatic possibility of tapping into the quantum vacuum. Quantum field theory suggests that even in its lowest possible energy state, the vacuum is alive with zero-point energy, a non-radiating electromagnetic field in a constant state of flux. What if we could interact with this quantum foam? What if we could apply an electromagnetic zero-point field to a dielectric material, affecting its inertia and thereby creating an acceleration without any internal stress or strain on the material itself? This is a profound leap, suggesting that the very stuff of matter, the elementary charged entities called partons that compose it, could be influenced by this ubiquitous, hidden energy. These ideas are, without doubt, theoretical and deeply speculative. They inhabit the very edges of our understanding, where physics itself grapples with unanswered questions. The potential thrust, the maximum velocity achievable through such methods, remains entirely unknown. Experiments designed to explore these concepts, to seek analogs for force generation from zero-point energy fluctuations or electrogravitic interactions, have been conducted in laboratories. But the results, as of now, remain inconclusive, difficult to replicate, and consistently challenged by the fundamental principle of momentum conservation. This is the central challenge, the grand paradox at the heart of field propulsion based on the physical structure of space. Without a clearly identified external momentum exchange medium, without something tangible to push off, how can such mechanisms be reconciled with the ironclad law of momentum conservation? If our system is truly closed, how can it generate a net thrust without violating one of the most fundamental tenets of physics? This question leads us directly to the distinction between open and closed systems, a distinction that forms the bedrock of viability for any propulsion concept. Open systems, as we've discussed, find their legitimacy in their interaction with the environment. Solar sails push against photons from the sun, magnetic sails against the solar wind. They exchange momentum, transferring it to or from the surrounding cosmos, thereby upholding the conservation laws. Electrodynamic tethers, for instance, generate thrust by interacting with a planetary magnetosphere and ionosphere, essentially pushing off the magnetic field lines. These are proven terrestrial examples in magnetohydrodynamics, where electromagnetic fields act on conducting fluids, accelerating them to generate thrust, a fluid equivalent of electric motors. The EMS 1 and Yamato 1 are real-world ships that have demonstrated this principle, propelling themselves by accelerating seawater. The extension of such principles to space, through concepts like Lorentz-actuated orbits or atmosphere-breathing electropropulsion, seeks to use ambient plasma as the working fluid, avoiding the need for onboard propellant by collecting and accelerating particles from the sparse environment. But the truly mind-bending concepts, those that aim to manipulate spacetime itself or tap into the quantum vacuum, fall into the realm of hypothetical closed systems. These are the reactionless drives, the ideas that purport to generate thrust without any external interaction, without expelling anything, without having any identifiable external momentum channel. And it is precisely here that they collide with the conservation of momentum. This law, implicit in the works of Newton and Galileo, arises from a deeper principle: the spatial translation symmetry of the laws of physics, elucidated by Noether's theorem. Any propulsion system that claims to produce net thrust in a closed system without external interaction challenges this fundamental symmetry. It would require physics beyond our current standard model to be viable. Yet, the allure of such a breakthrough is undeniable. The promise of unlimited velocity, of journeys unconstrained by the finite mass of propellant, continues to motivate exploratory work. NASA's Breakthrough Propulsion Physics program, for example, explicitly set research goals that included propulsion that requires no propellant mass. These programs, along with initiatives like the NASA Institute for Advanced Concepts, fund studies on ambient plasma wave propulsion, all-vane wave coupling, and other non-chemical pathways, all while acknowledging the profound theoretical challenges and the unresolved consistency issues. The history of advanced propulsion research reveals a recurring cycle, a surge of optimism when chemical rockets hit their theoretical limits, followed by classification efforts to categorize exotic schemes. Early surveys grouped propulsion into thermal, field, and photon categories, with field broadly referring to approaches that might exchange momentum or energy with external reservoirs. These were seen as long-range prospects, but they kept the dream alive. By the late 1990s, NASA's Breakthrough Propulsion Physics program formally tackled the question: could propellantless propulsion be consistent with conservation laws? Could momentum exchange with ambient plasmas or fields truly substitute for mass ejection? The answers, even now, are not definitive. What is clear is that the further we stray from identifiable external interactions, the deeper we plunge into the unknown, where the very rules of the universe might need to be rewritten. This brings us back to the core of the debate: open versus closed systems. The viability of any open, field-coupled concept depends entirely on the strength of its coupling to the surrounding environment. How effectively can a magnetic sail interact with the variable density of the solar wind? How much thrust can an electrodynamic tether generate in the weak magnetic fields far from a planet? These are practical engineering questions. In contrast, the viability of a truly closed, reactionless drive hinges on a radical reevaluation of fundamental physics. It would imply a profound secret in the universe, a loophole in the conservation laws that we have yet to discover. So, as we gaze upon the vastness, we are left with a tantalizing thought. Is space truly an empty canvas, or is it a hidden engine, waiting to be understood and harnessed? Can we learn to surf the quantum foam, or ride the very ripples of space-time. The quest for field propulsion, in its most profound sense, is a quest to understand the ultimate frontier, not just of space, but of physics itself. From the ambitious visions of the 1960s to the meticulously framed inquiries of NASA's breakthrough propulsion physics program, the quest for field propulsion has been a decades-long journey, constantly pushing the boundaries of what we understand about the universe and how we might traverse it. Initially, as chemical rockets approached their theoretical limits, aerospace engineers and scientists began to categorize alternative propulsion concepts into broad headings. You had thermal, encompassing ideas that heated a working fluid to extreme temperatures, photon, which focused on pushing off light itself, and then field, a rather expansive umbrella for anything that might interact with external forces or media. These early classifications, emerging from contractor reports for the Air Force and NASA in the 1960s, recognized that truly revolutionary space travel would require moving beyond the conventional expulsion of mass. The term field in those early days referred broadly to approaches that could exchange momentum or energy with external reservoirs. Think plasmas, magnetic fields, or even directed energy sources. These concepts were largely considered long-range prospects, not immediate flight systems, but the seed of field propulsion was planted and the terminology persisted through successive planning cycles. It was a testament to the enduring dream of a future where we wouldn't need to carry all our fuel with us. As the 1960s transitioned into the 1990s, some aspects of electric and electromagnetic propulsion did mature experimentally. We saw systems with strong field components even begin to fly in limited operational roles, yet they still relied on expelling propellant, albeit in a highly efficient manner. But the truly speculative end of the spectrum, the dream of a craft that could push off against the environment without carrying any reaction mass at all, that remained firmly in the realm of research. Reports from institutions like the Air Force Rocket Propulsion Laboratory in 1972 and later studies from the Jet Propulsion Laboratory in 1975 and 1982 formalized this division. They published roadmaps that once again categorized advanced concepts into thermal, field, and photon classes. These reports began to emphasize infinite specific impulse systems, propulsion methods that would obtain both working fluid and energy directly from the ambient environment. The hope was that new advancements in fields like lasers and superconductors might breathe new life into previously discarded concepts, perhaps even giving rise to a new generation of laser propulsion or ramjets that could scoop up interstellar hydrogen. By the late 1990s, this style of classification had been fully embraced by NASA's breakthrough propulsion physics program, often referred to simply as BPP. This program, which explicitly aimed to push the boundaries of known physics, posed fundamental questions. Could propellantless propulsion be made consistent with conservation laws? And could momentum exchange with ambient plasmas or fields truly substitute for the traditional ejection of mass? These were not trivial questions. They challenged the very foundations of how we understood force and motion. Later, the NASA Institute for Advanced Concepts, or NJC, continued this line of inquiry, funding studies on concepts like all-vane wave coupling and other plasma interactions, exploring whether they could indeed provide a quasi-propellantless thrust. Across all these programmatic efforts, leading researchers at the physics frontier acknowledged the conceptual appeal of field propulsion. But they also consistently stressed the unresolved consistency issues that arose when no clear external momentum channel could be identified. The universe, it seemed, wasn't quite ready to give up its secrets on a silver platter. The scope and terminology used in these various sources often shifted, depending on context. Contractor studies for NASA, for instance, grouped advanced options under headings like thermal propulsion, field propulsion, and photon propulsion, with field specifically covering those externally powered and field interactive concepts that went beyond conventional rocketry. Meanwhile, Surveys on electromagnetic propulsion often treated plasma and ion engines, even those employing strong electromagnetic fields, as electropropulsion because they still fundamentally expelled reaction mass. However, program statements from the physics frontier, particularly those from the BPP, define a much more aspirational target: propulsion that requires no propellant mass. This ambitious goal motivated studies into momentum exchange via ambient fields and other non-chemical pathways, explicitly aiming to separate physically testable ideas from non-viable claims. The BPP program, established in 1996, set forth three headline goals: propulsion with no propellant mass, achieving the maximum physically possible transit speeds, and discovering breakthrough energy methods to power such devices. It framed the field propulsion question in terms of fundamental physics limits and testable claims, pushing the scientific community to rigorously examine every theoretical possibility. Similarly, NIAC funded studies that explored using ambient plasmas and magnetic fields, like the solar wind or planetary magnetospheres, to generate thrust without expelling onboard propellant, including those fascinating all-vane wave coupling concepts. In 1983, a NASA contractor survey on beam-powered propulsion, titled Advanced Beamed Energy and Field Propulsion Concepts, further argued that future missions would inevitably require propulsion capabilities far exceeding chemical rockets. This report examined systems where power is transmitted to the vehicle, think laser, microwave, or particle beams, thereby decoupling the onboard energy source from the actual thrust production. It also organized prospects into those familiar thermal, field, and photon classes, identifying enabling technologies such as higher current superconductors or even the theoretical room temperature superconductors as potential breakthroughs for field interactive designs. The report acknowledged the historic funding swings in advanced propulsion research, noting initial surges in the 1960s and early 1970s, followed by sharp reductions after 1975. This ebb and flow of resources significantly impacted the pace of research in these highly speculative, yet potentially game-changing areas. A significant 1972 Air Force Rocket Propulsion Laboratory study, for instance, explicitly aimed to explore transitions beyond chemical propulsion, hoping to stimulate the development of more advanced performance systems by the end of the 20th century. This report categorized advanced propulsion into thermal, field, and photon domains, evaluating each for its performance potential. Crucially, it emphasized a return to the unrestricted creativity and free thinking that characterized propulsion research in the late 1950s and early 1960s, a spirit of open-minded exploration that is still vital today. Among its primary conclusions, the AFRPL report highlighted that more intensive energy sources, such as nuclear power, offered performance improvements up to 5 orders of magnitude greater than chemical sources. It urged propulsion researchers to prioritize infinite specific impulse systems that could obtain both working fluid and energy from the ambient environment, promising truly exceptional performance potential. For field propulsion specifically, the study identified technological breakthroughs like higher current density superconductors, metallic hydrogen, or room temperature superconductors as potentially enabling innovations. The argument was that improvements in technologies like high-power lasers or new energy transfer methods could truly revitalize previously discarded propulsion ideas, including laser propulsion and those elusive infinite ISP ramjets. Later, in 1984, the physicist Robert Forward extended these beam sail studies to the interstellar scale, suggesting that phased solar system lasers could impart sustained acceleration to ultralight sails across astronomical distances. He calculated that such a system might accelerate a probe to about 11% the speed of light, potentially reaching Alpha Centauri in roughly 4 decades. This brought the timescale of an interstellar flyby tantalizingly within a human lifetime, a truly revolutionary concept. By 1993, a NASA review by Myers on electromagnetic propulsion identified 3 main types of systems that, while still expelling propellant, use strong electromagnetic fields in their operation: pulsed plasma thrusters, magnetoplasmodynamic thrusters, and pulsed inductive thrusters. Pulsed plasma thrusters, or PPTs, had already seen use for attitude control and drag makeup on satellites. Magnetoplasmodynamic devices, or MPDs, had flight heritage in experimental regimes, and pulsed inductive thrusters, or PITs, sought to reduce electrode erosion limits through inductive coupling. This review emphasized the benefits of these systems, such as high specific impulse, precise impulse bits, and robustness, alongside their unresolved issues like efficiency, cathode wear, and spacecraft power and integration. It framed them as electric propulsion architectures where strong fields were central to their operation, but where the fundamental principle of expelling mass for thrust remained. Pulsed plasma thrusters, in particular, represented the earliest class of electromagnetic propulsion systems to achieve operational deployment in space, beginning in the 1960s. These thrusters generated thrust by ablating a solid propellant with an arc discharge and then accelerating the resulting plasma using Lorentz forces. They were compact, low power, and pulsed, making them suitable for satellite positioning and drag compensation. The Soviet Zond 2 Mars mission in 1964 even marked the first planetary use of electropropulsion, followed by successive U.S. deployments. PPTs remain relevant for low-mass spacecraft requiring precise impulse bits, though scaling them to higher power levels has continued to present technical challenges. Magnetoplasmodynamic thrusters, or MPTs, also emerged as a major class of electromagnetic propulsion, investigated for both quasi-steady and steady-state spaceflight applications. These operate through the Lorentz force, generated by the interaction of discharge currents with self-induced or externally applied magnetic fields. MPD thrusters were among the very first electric propulsion devices to actually fly in space. Initial experimental campaigns explored both self-field and applied field configurations, with development advancing through international programs aimed at supporting high-power planetary missions. While technological challenges, including efficiency optimization and cathode erosion, persist, MPD thrusters continue to be a key pathway towards scalable, high-thrust, long-duration propulsion architectures. Pulsed inductive thrusters, or PITs, represent another form of electromagnetic propulsion, specifically developed to overcome the erosion and lifetime limitations of electrode-based systems. By inducing plasma currents through time-varying magnetic fields, PITs accelerate neutral propellants without requiring physical contact between conductors and the plasma. This concept originated in the late 1960s and evolved through successive experimental designs focused on performance scaling, circuit optimization, and propellant compatibility. Although no PIT system has yet flown in space, this class of thrusters remains of significant interest due to its potential for high-efficiency, long-duration propulsion with minimal material degradation, particularly in missions requiring flexible propellant selection and reduced contamination risk. Returning to the physics frontier, the BPP memo from NASA, and later work by Minami and Musha, explicitly framed research questions at the very limits of physics: no propellant propulsion, ultimate transit speeds, and breakthrough energy production. The explicit goal was to distinguish between physically testable ideas and those considered non-viable claims. Minami and Musha, for instance, surveyed a class of proposals that posit a substantial physical structure of spacetime or the vacuum itself, macroscopic in the realm of general relativity, microscopic in quantum field theory. They investigated whether asymmetries in massless fields or vacuum-medium interactions could yield thrust without mass expulsion, though they reported that such systems remained theoretical and controversial. With ongoing but inconclusive experiments and persistent consistency concerns with momentum conservation. This dual framework places field propulsion concepts at the intersection of general relativity, which treats spacetime as a dynamic geometry, and quantum field theory, where the vacuum is thought to host fluctuating fields and latent energy. Several mechanisms have been theorized to achieve such coupling, including vacuum polarization, direct manipulation of spacetime curvature, and asymmetrical force distributions generated by interactions with massless fields. However, None of these have been experimentally validated, and laboratory-scale studies attempting to find force generation analogs, such as zero-point energy fluctuations and electrogravitic interactions, have yielded inconclusive and often difficult-to-replicate results. A central theoretical challenge remains the reconciliation of these concepts with the fundamental conservation of momentum, as without a clearly identified external momentum exchange medium, such mechanisms would violate fundamental physical laws. ANIAC Phase 1 study in 2011 evaluated ambient plasma wave propulsion, focusing on momentum exchange with existing space environments like the solar wind or magnetospheres, via waves such as alphane modes, alongside sails and electrodynamic tethers. These were considered candidates for propellantless or quasi-propellantless thrust. The authors highlighted both the undeniable appeal of not carrying onboard reaction mass and the very real limits of such concepts, including their technical immaturity and significant power and sensitivity shortfalls for achieving substantial maneuvering capabilities. Throughout all these historical and ongoing research efforts, conventional rocket and electric systems have remained the baseline for operational missions, their performance bounded by the clear energy and momentum balances described in standard propulsion texts. However, field-coupled approaches that exchange momentum with external photon, plasma, or magnetic reservoirs are consistent with conservation laws, but only when that external medium genuinely provides the countermomentum. Claims of net thrust in closed systems without such an external exchange continue to conflict with the momentum conservation framework that is so consistently emphasized in physics frontier reviews. Another complementary way to frame performance is through mission energetics, rather than simply hardware categories. This approach shifts the emphasis from individual devices to the delicate balance between energy, mass, and external coupling. In this view, field-coupled systems inherently trade carried propellant mass for a dependence on ambient fluxes and on the vehicle's ability to efficiently couple power into those fluxes. Solar sails, for example, scale their acceleration with solar irradiance and the sail's area-to-mass ratio. This means sails highly reward extreme reductions in aerial density and very precise attitude control. However, they offer little thrust authority in deep shadow or far from the sun, where the solar flux drops dramatically with the square of the heliocentric distance. Magnetic or magnetospheric sail concepts similarly scale with the dynamic pressure of the impinging plasma and with the effective standoff distance of the vehicle's magnetic field structure. This leads to a design space dominated by factors like coil mass, current, and the incredibly complex control of magnetic topology in highly variable plasma conditions. A recurring theme in this research is that open systems have the potential to move the propellant problem either into the environment itself or back to the ground segment. Beamed energy concepts, for instance, externalize the entire power plant to a ground or orbital transmitter, while the vehicle primarily provides an absorber, converter, and steering mechanism. This significantly reduces carried mass, but imposes stringent line-of-sight and infrastructure constraints, and introduces entirely new challenges related to beam riding guidance and safety. In stark contrast, conventional electric propulsion internalizes both energy conversion and propellant handling. This simplifies operations in sparse environments, but at the cost of carrying reaction mass and often very significant power processing hardware. Ultimately, the conservation of momentum remains the absolute fundamental boundary on all propulsion concepts. Devices that attempt to produce thrust without propellant or any other exchange of momentum are simply not consistent with known physics. Academic reviews consistently echo this conclusion, stating that propulsion systems which claim to generate net thrust without reaction mass or a clear interaction with external fields are regarded as inconsistent with the current framework of physics. Environment-coupled approaches, such as sails, tethers, or plasma wave coupling, remain physically possible, but only if the method of external coupling is strong enough to provide a truly useful amount of thrust. The decades-long quest for field propulsion has been a relentless pursuit of breaking free from the tyranny of the rocket equation, a profound exploration of the fundamental laws that govern motion and energy. While many of the most audacious dreams remain firmly in the theoretical realm, the journey itself has deepened our understanding of the universe, revealing both its stubborn adherence to its physical laws and the tantalizing possibility that, just perhaps, there are still new ways to whisper to the cosmos, to nudge it, and to set sail on its currents without ever needing to carry a drop of fuel. The future of space travel, if it truly aims for the stars, almost certainly depends on finding a way to harness the very fabric of space itself. And so, our journey through the intriguing world of field propulsion draws to a close. We've explored the foundational physics, glimpsed the triumphs of sails and tethers, and peered in the most speculative realms where spacetime itself becomes our engine. The quest for truly propellantless travel continues to inspire, pushing the very boundaries of our understanding. If this deep dive into the cosmos resonated with you, please consider liking this video, leaving a comment with your thoughts, sharing it with curious minds, and subscribing to join our community for more explorations. What other mysteries of the universe would you like us to unravel next? Until our next cosmic contemplation, keep looking up